Okay, so for this one, we have a particle with a charge of, and for this, for some of the characters that don't seem to be coming in properly, I'm just going to use charges, at least my best guess for some of them. So we have a charge of 1.9 times 10 to the minus 6 coulombs. And we're moving it from point A, from point A to point B, along a distance of 0.28 meters. And it experiences a constant electric force, and its motion is along the line of action of the force. So we've got an E field that points in the direction from A to B. And then we're given that the UA minus UB is 13 times 10 to the minus 4 joules. And then we're asked to find the magnitude of the electric force. So it gives us it like this, which is kind of funny because delta U is always final minus initial, so it should be UB minus UA, which is minus 13 times 10 to the minus 4 joules, which is good because it means that our potential is going down, which it always does. So we always go from high to low. So the fact that it's negative means that we're doing that. So we're asked to find the magnitude of the electric force. I always remember this little square here. So in going from the potential to the force, we take derivatives with respect to distance, and in this case we can just leave it in one dimension because we're just moving in one dimension. And we're also asked to find the magnitude of the electric field, and so moving from electric field to force, we multiply by charge. And then the other side of the square is the potential, which I'm just going to fill in for completion, like that. So this is kind of the square I use to remember all this. So if minus du by dx is the force, then so that actually makes it easy on us. So our as long as our force is constant, which it says it is, then our force is just minus delta U over delta X. So just taking the differentials and moving them to a delta. So in this case, it would just be 13 times 10 to the minus 4 joules over 0.28 meters, which comes out to be 4.64 times 10 to the minus 3. And now a joule is a kilogram, or is a Newton meter, I should say. So a Newton meter divided by a meter is just a Newton. And so that also kind of validates that we're doing something right here, just because the units work out. It doesn't mean it is right, but it's a pretty good indicator. And so then for B, so looking at our little square here, F is just QE. So then E is F over Q, which is just 4.64 times 10 to the minus 3 newtons over our charge, which is 1.9 times 10 to the minus 6 coulombs, which comes out to be 2,443.6 newtons per coulomb. Okay, and so there's our force and our E field. Okay, now if we check through the solution here, so our charge is starting at negative, which isn't so great. dW is F dot dr, so we're getting the same force, which is good, but their delta U is also opposite. But they're also computing work. So direction is the force. Not quite, but it's okay. And then the force is coming out to be massive. Why is that? 10 to the 4. It should be 10 to the minus 4, I see. Okay. So there's just a few sign errors throughout here. The E field should be from B to A, taking things in the proper direction. So all the numbers are coming out similar, but I'm just going to say several sign errors and exponent errors. And I'm just going to say it's incorrect.